Hey guys, and welcome back to another video. In this video, we'll be talking about the mean value theorem. Alright, so let's get right into it. Alright, so to begin with, I'm just going to draw a graph of a function. So if we have some function on the interval a to b, and it looks like this, let's just say, so let's say this is like the graph of y equals f of x, right? So let's just draw the secant line through a and b, right? So we have secant line looks something like that, right? So if this is a, this is f of a, and then this is f of b right here. So let's find the slope of the secant line, right? Well, the slope of the secant line is pretty easy. It's just f of b minus f of a all over b minus a. This is slope secant. Okay, good. So, but now, like, it seems as if we draw the tangent line to the graph at this point right here, right? So let's just draw the tangent line to the graph of f at this point that I just drew. So it would look something like that. And my equation will cut off a little bit. Like that, right? So that's the tangent line at this point, and I'll call this point right here to be x equals c, let's just say. All right, so x equals c. But it seems as if this tangent line to the graph at c is parallel to the secant line, right? And so that would mean that they had the same slope. So, right? So that's just like, it seems that's the case. Well, all right, so let's just forget about the secant line for now. And let's just consider the tangent line. So what would be the slope of the tangent line if we didn't know that it was already equal to the slope of the secant line? Well, it's a tangent line, right? So therefore, the slope of the tangent line is just f prime of c. It is the derivative of f evaluated at c. So that's equal to slope of the tangent line. But from our drawing, these two lines are parallel, so that implies that these two lines should have the same slope. So basically, m tangent is equal to m secant. Or in other words, f prime of c is equal to f of b minus f of a all over b minus a. All right, so we get this equation. So that's good and all, right? So this worked out for our specific example of f right here. So we got that there exists some point in the interval a to b for which the derivative, or for which the slope of the secant line is equal to the slope of this tangent line. So that's good. But does there always exist such a c? So like if we're given any function f, continuous function f on a closed interval, does there always exist a point c in the interval such that the tangent line at that point is equal to the secant line at the endpoints? And that's exactly what the mean value theorem answers. All right, so our question was, does there always exist such a c? Right, does there always exist such a c? So the answer is yes. Yes, right? There does always exist such a c. And that's what the mean value theorem guarantees. So that's basically what the mean value theorem says. All right, so now I'm going to write out the formal definition of the mean value theorem, the formal statement, and we will break it down at the end. So the mean value theorem says that if you have some continuous function, so if f is continuous on some closed interval a to b, right? So f is continuous on some closed interval a to b, and it's differentiable on the open interval, so on open interval from a to b, because we require f to be differentiable because otherwise f prime of c wouldn't even exist, right? So that's why it's important that f is differentiable. But anyway, f is continuous on the closed interval and differentiable on the open interval, then there exists a c in our interval a to b such that f prime of c is equal to f of b minus f of a over b minus a. All right. So this is a very powerful theorem because it guarantees that the slope of the secant line, or like there exists a point C such that the slope of the tangent line at C is equal to the slope of the secant line. Okay, that's basically what this theorem is saying. So there is another special subcase of the mean value theorem. So there is a special subcase of MVT, and it's called Rolle's theorem. And Rolle's theorem is basically just the mean value theorem when f of b is equal to f of a, right? And the reason why it gets a special name, we'll see in a second. But basically, Rolle's theorem basically it says the exact same thing as the mean value theorem. So f must be continuous and differentiable. So then, if that's true, there exists a c and a to b. So there exists c and a to b such that f prime of c is equal to 0, right? So this is the case when f of a is equal to f of b in the mean value theorem. Because then this whole fraction just goes to 0, so f prime of c is equal to 0. But the reason this is so special is because we have that f prime of c is equal to 0. So if you remember from our previous video, the extreme value theorem, we showed that if f prime of some number c is equal to 0, that means that c is a critical point, is a critical number. And so that means that f must have like some type of extrema or something at x equals c. So that's why this is super important, is because the Rolle's theorem can help you guarantee or help you find critical points of f. All right, cool. All right, so now let's move on to some examples. All right, so this is our first example. So we have the height of a ball as a function of time is given by s of t equals negative 4.9 t squared plus 300, and t is in seconds. And part A is asking us to find the average velocity of the ball during the first 3 seconds. All right, so essentially, the first 3 seconds is the interval from t equals 0 to t equals 3. So we have to find the average velocity of the ball on this interval. So if we just strip away all like the physics terms and physics jargon like height and velocity and all this is really asking us to find is the slope of our s of t on this interval 0 to 3, right? So we just have to find the average rate of change of s on this interval. And so that's just equal to s of 3 minus s of 0 all over 3 minus 0. And this is equal to 255.9 minus 300 all over 3, which evaluates to negative 14.7 feet per second. All right. So the average velocity of the ball during the first 2 seconds is negative 14.7 feet per second. All right. All right. So this is part B. So part B is asking us if the instantaneous velocity during the first 2 seconds ever equals the average velocity in the first 2 seconds. And if so, when. All right. So in the previous part A, we calculated that the average velocity is equal to negative 14.7 feet per second. All right. So now let's see, what is this really asking us? Like stripping away all like the words and just putting this into math. What is this asking us? Well, if you recall from my linearization video, right? So that was 3.2. I said that the first derivative of position is equal to the instantaneous velocity, right? So if we take the derivative of our position of our position function, we get instantaneous velocity, right? And so that's this first part. So does the instantaneous velocity is basically just saying, does s prime of t ever equal the average velocity, so v average? But I'm not going to write it as v average. I'm going to write it as its expanded form, because remember, v average we saw in the previous part, in part A, this is just simply equal to s of 3 minus s of 0 all over 3 minus 0, right? At least on the interval from 0 to 3. So it's asking us this question, if f prime of t is ever equal to s of 3 minus s of 0 all over 3 minus 0. So does there exist some t in the interval from 0 to 3 such that it satisfies this equation? Well, this is exactly what the mean value theorem says, right? It says that if you have some intervals, in this case our interval is 0 to 3, then the average rate of change over this interval is equal to the instantaneous rate of change for some t inside of that interval, for some x inside of the interval. So yes, the answer to our first question, if the instantaneous velocity ever equals the average velocity, the answer is yes. So now we just have to find the specific time. Well, we know that this is just equal to negative 14.7. So all we have to do now is solve the equation s prime of t equals negative 14.7. Okay? All right, so we have the equation s prime of t equals negative 14.7. So let's go ahead and take the derivative of s now. So by the power rule, we can just find the derivative. It's simply just negative 9.8t. And setting that equal to negative 14.7, we get that t is equal to 1.5 seconds. All right, so the instantaneous velocity of this ball is equal to the average velocity of the ball on the interval from 0 to 3 seconds at 1.5 seconds. All right, so this is on the interval from 0 to 3 seconds. Just want to reinforce that. All right, cool. All right, so now let's move on to our next example. All right, so in our next example, we have two police cars. All right, so I'll just represent the police cars using these boxes. And suppose they're like by the road, so like they're in the grass right here. All right, and we know that the distance between the two police cars is exactly 5 miles. All right, and so then we have the road over here, and we have some truck that's passing through these police cars. So it's represented by this box right here. And we're given that when the truck passes through the first police car, so as the truck passes through the first police car, so first car, the speed of the truck is 55 miles per hour. All right. And then as the truck passes through the second police car, its speed is 50 miles per hour. So as it passes through the second car, its speed is 50 miles per hour. All right. And we're also given that the time it takes the truck to pass from the first car to the second car is 4 minutes. All right. So our time interval, I'll just call delta t, is 4 minutes. All right. And then furthermore, we're given that the speed limit on the specific road is 55 miles per hour. All right, so our speed limit is 55 miles per hour. So just at a first glance, it doesn't look like the truck ever violates the speed limit, right? Because it goes 55 miles per hour, it passes the first car, and it goes 50 miles per hour as it passes the second car. So, it's good. It doesn't violate the speed limit. However, we have to show that actually it does violate the speed limit, and we can do that using, well, the mean value theorem. And so this is how this goes. So our question is if the truck is speeding or not. So is the truck speeding? All right. So I'll call the time when the truck passes through the first car to be t equals 0 hours. And so that means that what is the time the truck passes through the second car? Well, we're given that it's 4 minutes, but we want t in hours. So let's just go ahead and convert 4 minutes to hours. And if you do that, you will get that t is equal to 1/15 hours as it passes through the second police car. All right. And then we know that the distance between the two cars is 5 miles. So now let's go ahead and find the average rate of change, or in other words, the average velocity of the truck as it passes through these two cars. So at the second police car, the truck has traveled a distance of 5 miles. And then over here, we'll say that it traveled 0 miles so far. And then all over the time interval of 1/15 hours. All right, so this is equal to 75 miles per hour. So 75 miles per hour is the average speed of the truck as it passes through the two police cars. Okay, so this is the average rate of change of the truck on the interval 0 to 1/15. All right, so then because our speed function, our velocity function of the truck, because that's a continuous and differentiable function, we can apply the mean value theorem. And the reason it's continuous is differentiable is because it doesn't like automatically jump from like 50 to like 70 miles per hour, right? It's like a continuum. It like slowly accelerates up there. All right. So that's why this is a continuous and differentiable function. So we can apply the mean value theorem. And what the mean value theorem says is that there exists some point in this, there's some time between 0 hours and 1/15 hours such that the instantaneous speed of the truck at that time was equal to 75 miles per hour. So if we let s of t be the speed, or we'll say let v of t be the speed of the truck, so be the velocity. So yeah, let v of t be the velocity of the truck. So then we know that v prime of t, the instantaneous velocity, or sorry. So we're gonna let s of t be the position of the truck. So let s of t be the position of the truck. So then that's why s prime of t is the instantaneous velocity, right? We just discussed that s prime of t is equal to v of t is the instantaneous velocity, right? So s prime of t, the instantaneous velocity, this is equal to the average velocity, which is 75 miles per hour, for some time t in our interval 0 to 115. So therefore, we know that the truck must have reached 75 miles per hour and thereby breaking the speed limit during some time interval. So even though it didn't break the speed limit when it passed through the two police cars, it definitely did somewhere in between, somewhere in the 5 miles in between the two police cars. It did. And we can't exactly find what t value that was because you don't have an explicit expression for s of t, but the fact that it did is like good enough. So like for example, the reason I find this intriguing is because if you this truck went to court and then they argued that I was only going at 55 miles per hour and 50 miles per hour, and like the police cars can like vouch for me or something like that, you can actually use the mean value theorem to show, wait, no, he wasn't. He actually did break the speed limit because there was some time in between the two cars where he went 75 miles per hour, right? So that's found that pretty cool that you can actually prove that the truck actually broke the speed limit, even though like the police cars, bystanders wouldn't have necessarily known that, right? But yeah, that pretty much wraps up this video on the mean value theorem. If you found this video helpful, please make sure to leave a like and don't forget to subscribe. I'll see you guys in the next video.